that would be fantastic. While they are doing that, a quick community service announcement. For those of you who are AGU conveners, today is the last day to input your invited speakers, so make sure you do that. Also, we do have abstracts due on August 3rd, and Survey does have a community-wide a session ongoing at AGU this year, and it's the science of exploration on the moon, asteroids, and moons of Mars. So with that said, we're about to have our first lightning round talk session. The lightning round talks are an opportunity for the next generation of lunar scientists, asteroid scientists, and moons of Mars scientists to come up and within 90 seconds give you a rundown of who they are, where they're from, and what their research is, why it's important to you, and why you should come visit either their poster or come listen to their talks. They do have 90 seconds, and I did put on here a lightning round talk, and this is what will happen to them if they go over those 90 seconds. So I will be back there monitoring that as we go forward. So we'll go ahead and get started, top of the list, with Ben.
Good afternoon. My name is Ben Hochman. I am a third-year PhD student in the Aeronautics and Astronautics Department at Stanford University, so just right up the road. And my particular focus is on how we can use the latest developments in robotics and automation for space exploration, and in particular doing robotic reconnaissance and achieving science objectives on the surface of bodies. So the project I'm going to be presenting tomorrow at 3:30 in this room, as well as a poster number 69, is on a project that seeks to enable a new kind of exploration on small bodies. Now, small bodies are very challenging in that they have a microgravity environment, which is much different than the environments such as Mars and the Moon, where we've sent rovers in the past. So we've developed this rover we call Hedgehog, and it's in essence a very small cube-shaped hopping rover that uses internal actuation via flywheels to controllably hop and tumble across the surface. And we do that in a controlled way so that it can enable scientific objectives that can only be fulfilled with targeted exploration. So for example, visiting certain spectral regions on Phobos that are particularly interesting. So we've studied the dynamics and verified through simulations and experiments on reduced gravity flights that it is indeed a controllable way of getting around. And we've also studied the autonomy behind it all. So if you're interested in any of that, or if you just want to play with robots, because I have a couple prototypes with me, they'll be at poster 69 at all of the presentations. Again, my name is Ben Hochman, and thank you.
Go ahead. Rapid fire.
Hello, everyone. My name is Nate Marks. I am an electrical and computer engineering undergraduate at the University of Colorado Boulder, and I work for the Center for Astrophysics and Space Astronomy there. So the reason I'm talking to you today is I want to present some research that my group has done over the past year related to telerobotics. So for some background, one of the proposed Orion mission concepts is to have a crewed Orion module orbiting around the L2 Earth-Moon Lagrange point with astronauts actually directly controlling rovers on the lunar far side. So what my team has done is we've actually created a system to simulate missions like this so that we can hopefully figure out what some of the problems are while we're still on the ground. So the system we created has two main parts. We have a video system where we can throttle certain network conditions to simulate an imperfect connection between the capsule and the rover, and then we had to build a rover that can actually operate in a harsh, somewhat analogous environment to the moon. So if that sounds interesting to you guys, or if you just want to drive our robot because we brought it, please come to poster 70. Thank you.
Hello, everyone. My name is Ben Melinkov. I'm a third-year undergraduate aerospace engineering major at the University of Colorado at Boulder. Nate Marks and I both work at an undergraduate research lab associated with the Center for Astrophysics and Space Astronomy. Our group's main interest is in teleoperations of rovers controlled by astronauts in orbit. In particular, we're interested in finding the minimum frame rate required for operators to successfully explore an unfamiliar environment. So in order to do this, we had to create an outdoor lunarscape. And in this lunarscape, we gridded it off and randomly scattered interesting objects. These interesting objects were simply just rocks with two identifiable criteria that the operators had to identify. So we collected some pretty good data, have some pretty interesting results that we'd love to share with you guys. So please come check us out at poster 72. Thank you.
Hi everyone, I'm Ngọc Trương and I'm from the University of Science and Technology of Hanoi from Vietnam. And now my study is focused on the water contents on ultralazentictile, which are the impact glasses derived from impact meltings of upper crustal rock that then ejected into space and form back and quenching. And the most interesting for me on tictile is that it is nicely connected with the problem of water on Phobos and Deimos by giant impact origin hypothesis. And what we suggest is that even the ultralazentictile with subject to intense heating is up to 2000 degrees Celsius of temperature. We travel ejected out from the Earth's atmosphere into exospheres. And although there high energy history, the tictile is also still containing water. And we suggest that even in the giant impact origin hypothesis for Phobos and Deimos, the original material forming Phobos and Deimos might have containing significant water. And that's also the main idea of my talk will be at 3:45 p.m. at the side room. And I hope that you will enjoy and join me for the talk. Thank you.
I'm Alessandra Springman. Some of you know me as Sandy. I just finished my second year at the University of Arizona in Tucson. I work on the OSIRIS-REx asteroid sample return mission, and I'm going to be talking about some heating experiments we did on carbonaceous chondrites and what elements were lost and how that can be used as a proxy for understanding the past thermal history of Bennu, which is the OSIRIS-REx target, as well as its past orbital history, the orbital history of other objects in the solar system like rock comets, and also applications for in situ resource utilization, such as how much sulfur you're going to get in water when you start vaporizing meteorites like Murchison, which is relevant if you're trying to get water off of asteroids and trying not to poison your astronauts or destroying whatever is going to be making rocket fuel. So I will be at poster 73 today. I'll be talking about the OSIRIS-REx asteroid sample return mission, the history of Bennu, and loss of volatile elements from carbonaceous chondrites. See you there.
Hello, my name is Max Kaler, and I am a sophomore at SoCal High School. I'm currently working on this Lunar Orbiter Image Recovery Project, or the LOIRP. The purpose of this project is to process and recover images from the 1966 and 1967 Lunar Orbiter missions. A use of these images is to provide a historical record of the lunar surface, but also to reference with the more recent LROC images to track changes in the lunar surface from meteorites and other events. My job personally is to compile the framelits by frame and image and run it through an autoassembler. Once the image is assembled, I open it up in Photoshop and I fix any errors in alignment to provide a scientifically accurate, high-quality image. My poster number is 79, and if you would like to speak with me, I will be here from 4:45 to 5:30.
My name is Evan Thomas, and I am in my final year of graduate school at the University of Colorado at Boulder, and I'm interested in micrometeoroid ablation in Earth's upper atmosphere. And the reason why I'm interested in that is because if we measure the micrometeoroids that are ablating in Earth's atmosphere, we can better understand the dust environment around the Earth, which can help mitigate emission hazards, as well as increase our understanding of dust evolution in the solar system. And the way that we measured, or the way that I study this is that I study it in the lab. We have a dust accelerator at the University of Colorado, which fires micron and submicron size dust particles from 1 to 100 kilometers per second. So that's well within the range of meteoric speeds. And we attach a pressurized chamber to the back end of the accelerator that simulates the ablation in Earth's atmosphere. And we have a suite of electronics that measures the plasma generation. And this tells us about the physics of the ablation process, which will hopefully increase or decrease the uncertainties in meteor radars that measure the real thing. And hopefully that will then increase our understanding of the dust environment. So again, my name is Evan Thomas, and I have a poster on this. It's number 12, and I'll be there tonight and tomorrow for the poster session. Thanks.
Can we get one more round of applause for all of our student speakers today? Okay, I think we're going to go ahead and try to get started at 3:30 with our parallel sessions.